Every day, telescopes around the world capture strange signals coming from deep space. Most have natural explanations: dying stars, black holes feeding, galaxies colliding. But some signals are so strange, so organized, that they make scientists stop everything they're doing. In 1977, we captured a signal so powerful and artificial that a scientist wrote, "Wow," next to it. We never heard anything like it again. Now think about this. If we, with our still basic technology, can send robots to Mars and probes outside the solar system, what could a civilization thousands or millions of years more advanced do? They could have invisible probes orbiting Earth right now, so small and advanced that we don't even know they're there. Subscribe to the channel, leave your like and comment from what part of the world you're watching, because now I'm going to tell you everything. What are the signals we get from space? They are light and radio waves that travel across the sky. Telescopes on Earth and in space catch these signals. People use machines to measure and record them. A signal can be very strong or very weak. A signal can last for a short time or for a long time. Signals can be red, blue, or many other colors in the light we can see. They can also be in light we do not see with our eyes. Radio waves, infrared light, X-rays, and other kinds of energy come from space. Each kind of light tells a different story about the thing that made it. A very hot object can make strong X-ray emission. Cold dust can glow in the infrared. Fast particles that move in a tight beam can make strong radio waves. A burst that lasts one moment may come from a different source than a long, slow change. People use many tools to find and study signals. Each tool sees one part of the light. Radio telescopes catch radio waves. Optical telescopes catch light our eyes can see. Infrared cameras catch heat and warm dust. X-ray instruments catch very high-energy light. Each tool has a lens, a dish, or a detector that takes in the light or wave. The device turns the input into an electronic signal. That signal becomes numbers and images in a file on a computer. Scientists open the files and read the numbers. They look at charts and pictures made from those files. Those charts show how bright the signal is and how it changes over time. They can show one color or many colors at once. A single file can hold thousands of numbers. Scientists measure how bright a signal is. They measure the color. They measure how long it lasts. They measure how the signal changes with time. They measure the frequency of a radio wave. They measure the direction the signal comes from. They test whether the signal moves in a pattern. They look for steady pulses that repeat. They look for sudden bursts that stop quickly. They look for slow changes that take many hours or days. A key step is to check if the signal came from Earth or from space. They ask if the signal could be radio noise from a phone or a radar on Earth. They check the data for errors from the instrument. They see if the signal is in files from other telescopes. If other telescopes saw the same thing at the same time, the signal is more likely real. They use many checks to rule out local causes. Finding a real signal follows a clear set of steps. First, record the data. Second, clean the data from noise. Third, measure the signal properties. Fourth, compare the signal to known sources. If the signal matches a known source, the work may end there. If not, the signal becomes a puzzle. Scientists then plan more tests and observations. Raw data can have many unwanted signals. Noise can come from the instrument, from the ground, or from satellites. Engineers remove known patterns of noise with software. Care is needed so a real signal is not removed. They set filters to keep the data clean and to keep real events. Sometimes a filter removes an odd event that could be real. Good practice is to test the filters on known signals. Brightness is measured in a way that gives a number for each time. Color or spectrum shows which colors or wavelengths are strong. Wavelength is the name for the color in radio or infrared or X-ray light. Timing tells how the signal changes with seconds, minutes, or hours. Scientists also measure the exact place in the sky. Precise place helps to point other instruments there. No single tool can show all parts of a signal. A radio telescope can show radio waves, but not X-rays. An optical telescope can show color in light we see. An infrared camera can show warm dust that is hidden in optical images. X-ray instruments find very hot places. When several instruments work together, they give a fuller picture. Teams plan joint observations and share the data. Telescopes on the ground are simple to repair and upgrade. Telescopes in space avoid the blur and the glow of the atmosphere. Space instruments can see wavelengths that do not pass the air. Both kinds of telescopes are needed. Ground telescopes can follow a target for a long time. Space telescopes can give very clear views in some bands. After a team finds a signal, they share the data with others. Other teams try to see the same signal in their files. Independent checks lower the chance of error. Data may be re-examined with new methods later. Old files can hold events that were missed. Careful records of time and place are important. A strong, steady signal is easy to find. A wide signal that covers many colors is easy to see. A source that repeats often is easy to confirm. Nearby objects give stronger signals. A weak signal can hide in the noise. A short burst can occur when no telescope is watching. A narrow radio beam can point away from Earth. A small, dark object can reflect very little light. Automatic software can remove odd patterns as noise. Human-made radio noise can cover weak natural signals. A single detection is not proof of a new kind of source. Teams try to repeat the observation. They test the signal with different tools. They share data and methods openly. Only careful work can turn a strange signal into knowledge. A radio file shows frequency on one axis and time on the other. Bright spots in that plot show where energy is strong. Optical images show how bright an object is and what color it has. Spectrum plots show lines that tell us which atoms are present. Radar echoes give a map of shape and motion. When a team finds an odd signal, they plan more observations. They ask other telescopes to look at the same place. They set long watches to catch repeat events. They change the time resolution to see fast or slow features. They check old files to find a past occurrence. Catalogs list many known objects and events. Scientists compare new signals to these lists. If the signal matches a catalog entry, the cause is known. If not, the signal is studied more closely. They test physics models to see if known laws can explain it. No instrument can see everything. Each instrument has a limit in sensitivity. Sensitivity is the faintest thing it can detect. Instruments also have a limit in resolution. Resolution is how close two sources can be and still show as separate. Some instruments are fast and others are slow. Slow instruments may miss very fast bursts. Watching the sky for a long time increases the chance to catch rare events. Many projects run surveys that last months or years. Long surveys build a record that can be searched later. Having many records helps to confirm that a signal is not a one-time error. Computers process large amounts of data quickly. Software flags events that look odd. Human experts inspect flagged events. Human review catches errors that machines miss. Teams also design the tests and decide what is important. Earth is full of radio signals from many devices. Television, phones, and radar add to the background. Researchers set aside protected radio bands where no one should transmit. They still must check for interference. A strong path to certainty is to see the same event in different ways. For example, a radio burst and an optical flash at the same place and time make a strong case. Spectra can show the chemical makeup and help find the distance. Radar can show shape and motion for nearby objects. Scientists use models to predict what a natural source will make. They compare the data to these predictions. If the match is good, the source is likely known. When no model fits, scientists write new ideas and test them. Some signals take time to understand. A single odd event may not repeat for a long time. Teams must keep watching and keep testing. Patience and steady work lead to reliable knowledge. Signals from space come in many forms. Telescopes and detectors catch parts of this range. Data become files of numbers, charts, and images. Scientists clean the files and measure the key properties. They compare the signals to known sources and to models. Many checks and many instruments make a finding strong. It is a careful and step-by-step process. Knowing how we detect signals helps us judge what made them. Patterns of color, timing, and strength point to different causes. When a signal does not match any known cause, it becomes a puzzle to study more. It is the work of many teams and many tools. This chapter has shown the basic steps and the plain tools people use to find and test signals. A clear checklist helps teams follow each step. Record with accurate time and location. Note the instrument settings and the weather if the telescope is on the ground. Save raw files and processed files. Run noise removal with care. Measure brightness, color, time, behavior, and position. Compare to catalogs and to simple models. Ask other teams to look at the same data or to observe the source. Keep careful notes of each test and result. Many false signals come from human devices. Airplanes have radios and lights that can show up in data. Satellites pass overhead and can send signals. Microwave ovens and some lab equipment can cause bursts. Checking the time and the location often shows if a human device caused the event. Teams use lists of satellite paths and known radio sources to test for this. Some events do not match any known natural or human source. Then, teams broaden the search and use many instruments. They keep careful records and share all data. Long-term study may reveal a faint pattern. Patience and method give the best chance to solve the puzzle. New instruments make fainter signals visible. Faster computers let teams search more data. Networks of telescopes can watch more of the sky at once. New methods can find signals that were missed before. Better sharing and open data speed the checks. Studying signals teaches us about stars and galaxies. It shows how matter and energy behave in space. A clear, unexplained signal can open new knowledge. It is important to be careful and to follow the steps here. Always note the strength, the color, the time, behavior, and the position. Strength tells how much energy arrived. Color or wavelength shows the physical process that made the light. Time behavior helps to separate steady sources from bursts. Position points to a host object or region. Teams must stay organized and learn from each case. A clear log of methods and results helps others confirm the work. Public notes and shared files let many teams inspect the same data. Teaching new students the simple steps keeps the work strong. We accept that some puzzles take much time to solve. Careful measurement and patient study are the tools we trust. Global networks of observers help to confirm events quickly. A team in one place may call teams in other places. They ask them to point a telescope or to check old files. Fast response can catch repeat activity that might stop quickly. More eyes and more ears make a test stronger. Keeping raw data for years is useful. New methods may find signals that old methods missed. Teams often reprocess data with new software. This work can turn old files into new discoveries. Train new people to follow the checklist. Show them how to record time and position. Teach them how to test for local interference. Give them practice with known signals so they can spot real events. Use clear rules for how to report an unusual finding. Placing some instruments in space reduces human-made noise and the effects of the atmosphere. Small sensors can run long and send data when conditions are right. When a team has strong evidence, they prepare a clear report. The report lists the time, the place, the instruments, and the tests. It gives the data files or a safe link to the records. Clear language helps other teams check the work. Public channels may be used after careful checks. A signal can ask for many kinds of skills. Engineers check the instruments. Software experts process the data. Astronomers measure and interpret the signals. Chemists may help with surface spectra. Physicists test models of energy and motion. Teams that mix skills do better work. Many questions remain, and steady watch is the answer. A careful search takes years and many attempts. The path to discovery is slow but solid. We document each step and we learn from each test. The goal is clear knowledge. Keep watching with many instruments. Keep testing methods and records. Keep sharing data with all teams. In this way, small signals from space may become clear. The work is open and shared, and it grows with time. This careful and steady process is our best way to learn the messages that the sky sends us over time, every single day. Keeping many instruments watching the sky helps us know what makes strong signals. The sky gives us many kinds of light and radio waves. Each kind of source makes a pattern. These patterns help scientists name the source. Some sources give steady light, some give pulses, some give sudden bursts. This chapter lists the common natural sources. It explains what each source gives us in radio, visible light, infrared, and X-rays. It shows how time, color, and strength point to the cause. Stars make a lot of the signals we see. Many stars shine with steady light for long times. Some stars change their light over days or months. These are variable stars. Their light can grow and fall in a pattern. The pattern can repeat. If the light comes up and down in a steady way, the source is a regular variable star. Other stars end their lives in a bright way. A star that dies can explode. The explosion can make a sudden bright object in visible light. The bright light can last for weeks or months. The explosion also sends out radio waves and X-rays. The light from the explosion can move into space and light nearby gas. That gas can glow in many colors. Over time, the glow fades and changes. The shape of the brightening and the fade helps scientists know the kind of explosion. Neutron stars are one common source of strong signals. A neutron star is a tiny, very dense star left after a large star dies. It can spin very fast. If it has a strong magnetic field, it can send out pulses of radio waves. These pulses arrive like a steady beat. Some neutron stars pulse many times each second. Others pulse only a few times each second. The pulse repeats with a constant time between beats. This steady repeat makes a clear signature. Scientists can measure the time between pulses. They can measure the radio frequency and the strength of each pulse. These measures give the distance, the rotation speed, and the environment around the star. A special kind of neutron star is a magnetar. A magnetar has an extreme magnetic field. It can make sudden, very bright bursts in X-rays and gamma rays. These bursts can be short and intense. They can also make radio outbursts. The timing and the energy of these bursts help scientists know that a magnetar caused them. Black holes also make strong signals. A black hole is an object with very strong gravity. Matter that falls toward a black hole heats up. The hot matter glows in X-rays and visible light. If the black hole feeds on a steady flow of matter, the glow can be steady. If the flow varies, the light can flicker. Some black holes sit at the center of a galaxy. These active centers can shine for a long time. They can send out jets of particles. The jets make radio waves. Jets can also make X-rays and gamma rays. The pattern can be steady or can vary over hours, days, or longer. When two galaxies move together and crash, the event makes wide and long signals. Colliding galaxies can make many new stars. New stars can form in clouds of gas. The new stars can send out ultraviolet light. Over time, the light from many new stars makes the galaxy brighter. Collisions can also feed the central black holes. The result can be strong and long activity. The signals can come in radio, visible, infrared, and X-rays. The time changes are slow. They can last for many millions of years in total. The change we see can be over years or decades as new bright regions develop. Gas clouds and dust also send signals. Cold dust shines in infrared light. Warm dust shines more. Molecules in the gas can emit thin lines of radio or infrared. These lines appear in narrow parts of the spectrum. They tell us which molecules are present. Some gas clouds host natural masers. A maser makes a very bright, narrow radio line. It can be as strong as the emission from a star in radio waves. Masers come from specific molecules in special conditions of heat and density. Jets of fast particles make radio and X-ray signals. When particles move near the speed of light in a magnetic field, they make a smooth radio emission called synchrotron emission. This emission covers many wavelengths. It can be steady or it can vary. Jets can come from black holes or from young stars that push matter out into space. The shape of the radio signal and its spectrum help find the jet source. Cosmic rays are charged particles that travel through space. When they hit gas or dust, they can make X-rays or gamma rays. High-energy collisions can light up a region in these bands. A burst of gamma rays can show an extreme event. The pattern and the energy range point to powerful processes. Gamma ray bursts are some of the most energetic short events. A burst can send a flood of gamma rays for a short time. The initial burst can last a few seconds or a few minutes. After the first flash, an afterglow can follow in X-rays, visible light, and radio. The afterglow can fade over days to months. Two main causes can lead to such bursts. One is the death of a very massive star. The other is the merger of two compact objects, such as two neutron stars. The timing and the presence of an afterglow help scientists decide the cause. Supernova remnants are the gas left after a star explodes. The remnant glows in radio and X-rays for a long time. The glow comes from hot gas and from particles that move in magnetic fields. Remnants can show structures that move slowly over years. Their spectra show emission lines that tell which atoms are present. These lines often include oxygen and hydrogen and heavier atoms. The sun gives many kinds of signals that affect our instruments. Solar flares can burst in X-rays and radio. The sun can also send a stream of charged particles. When those particles reach planets, they can make auroras and radio noise. Solar bursts are common. They can be short or can last for hours. Instruments that study distant sources must check for solar activity that might confuse data. Planets can make signals too. Jupiter makes strong radio waves. The signal comes from the planet's magnetic field and from the charged particles that flow around it. Planets with strong magnetic fields can make radio emission. The Moon reflects radio waves and visible light. Small bodies like asteroids can reflect sunlight. Their reflected light can be faint. Radar can probe nearby rocks and return echoes that show shape and motion. Many natural sources show a clear fingerprint in the spectrum. A spectrum is a record of how bright the signal is at each color or each wavelength. Atomic and molecular lines in a spectrum show which elements and molecules are present. The position of a line can shift in wavelength. The shift tells the motion of the source along the line of sight. A line shifted to longer wavelengths shows the source is moving away. A line shifted to shorter wavelengths shows the source is moving toward us. The amount of shift gives a speed. Timing patterns also give strong clues. A steady beat holds a constant time between pulses. Pulsars show that steady beat. A repeating flare that returns every few days or months points to an orbital motion. An irregular burst that does not repeat can be a one-time explosion. The length of the burst matters. A very short burst of a few thousandths of a second points to a compact and fast source. A burst that lasts many days points to a large and slower process. Dispersion is a property that affects radio pulses. When a radio pulse travels through clouds of charged gas, the lower radio frequencies slow down more than the higher frequencies. The result is that the high-frequency part of a pulse arrives first, and the low-frequency part arrives later. Measuring this delay gives a measure of how much charged material the signal passed through. That measurement helps estimate how far away the source is. Dispersion is a key tool for signals that are brief in time. Polarization gives another tool to identify sources. Polarization tells how the electric field of the light or radio wave is oriented. Strong magnetic fields can polarize the light. If the signal is highly polarized, the source likely has strong magnetic fields or complex environments. Astronomers keep catalogs of known objects and sources. These catalogs list the position, the spectrum, the variability, and other properties. When a new signal appears, scientists compare the location and properties to the catalogs. A match often tells the likely source. If a signal falls on the position of a known pulsar, the identification is strong. If the signal comes from the region of a known active galaxy, the cause is likely linked to that galaxy. Surveys map the sky in many bands. Radio surveys make maps of radio sources. Optical surveys catalog stars and galaxies that shine in visible light. Infrared surveys map the heat from dust. X-ray surveys find hot gas and accreting objects. Each survey finds many sources and builds a baseline. When a new event appears, scientists check the survey maps. The maps help to find whether the source is new or has been there and was steady. Some natural signals repeat in a predictable way. Pulsars repeat with a steady beat. Variable stars repeat in cycles. Planets occult a star at a known time, and the dimming repeats each orbit. Regular repeats make identification easier. Other signals are one-time events. Supernovae and gamma-ray bursts can be one-time or rare events in a given place. One-time events need fast follow-up. Teams try to point many instruments to the same place soon after the event. The afterglow in other wavelengths often tells much about the cause. Energy and spectrum together tell the physical process. Thermal emission has a shape that rises with certain wavelengths and falls with others. Non-thermal emission from fast particles has a smooth spectrum across many wavelengths. Narrow spectral lines show atoms and molecules. Wide, smooth spectra show particle-driven emission. Scientists test each signal against simple physical models. They ask which process makes the energy at the observed wavelengths and on the observed time scale. If a model fits, the source is likely natural and understood. If the model does not fit, scientists search for other natural explanations or they recheck the data. Many known sources have been studied for decades. Those studies build a library of patterns. When a new signal arrives, scientists check for a match. A strong match ends the mystery. No match makes the signal a puzzle to study more. A clear case is a star that explodes. The light curve, the spectrum lines of certain elements, and the radio emission all follow a known pattern for a certain type of explosion. A match to that pattern gives confidence in the identification. A different case is a pulsar. The steady pulse period and the radio spectrum give a unique signature. A match to pulsar catalogs makes the name clear. Some sources are extended. A supernova remnant or a jet can cover a region of the sky. Extended sources show structure. The structure can change with time. Imaging at different wavelengths shows different parts of the structure. For example, radio images may show the jet path, while X-ray images show hot spots. Each image adds to the full picture. Understanding common natural sources helps to narrow the field when a new signal appears. It sets the baseline of what to expect. If a new signal matches a known pattern, scientists can move quickly to study details. If it does not match, they must work harder to confirm and to test new ideas. Many tools work together to build the picture. Radio, visible, infrared, and X-ray instruments each add a piece. Timing, spectrum, polarization, and position give key tests. Catalogs and survey maps give prior knowledge. Models help interpret the numbers. Careful checks for human-made interference are needed at each step. When a signal does not fit any known natural pattern, it becomes a deeper mystery. Scientists then plan longer observations and deeper tests. The work expands to include more instruments and more teams. The goal is to keep evidence strong and to find the best natural explanation before calling the event something else. We now know the common sources that make strong signals. The sky is full of stars, compact objects, black holes, gas, dust, jets, and explosive events. Each makes a limited set of signatures in time and spectrum. Knowing these signatures helps to sort the many signals we record. When a new signal does not match these signatures, it will be checked again and again until we have a clear answer. When a signal does not match known patterns, scientists pause and check many details. They do not rush to a conclusion. They test the data. They look for mistakes. They ask many people to help. Strange signals need careful work. A strange signal can mean many things. It can mean the data has an error. It can mean the signal came from Earth. It can mean the signal comes from a natural source we do not yet know. It can mean an artificial transmitter sent the signal. Each possibility must be tested. One kind of strange signal is a narrow tone in radio. The tone sits on a single narrow band of frequency. Natural sources rarely make a single thin tone that stays strong. Many human devices make such tones, so a narrow tone often raises the worry that the signal came from a human transmitter. Another kind of odd signal is a very short, bright burst. The burst can last only a few milliseconds. It can carry a lot of energy. These bursts can arrive with a sweep of frequency. The high frequencies may come a little earlier than the low ones. This sweep is called dispersion. It happens when radio waves pass through clouds of free electrons. The amount of delay gives a number. That number helps estimate how much charged gas the wave passed through. That helps say how far away the source might be. Some bursts repeat. Some do not repeat. A repeating source can show many bursts separated by irregular times. Each burst can have a different strength and a different shape. A non-repeating burst may show only once in a long record. That makes it hard to study. A famous old example shows how a single event can stay unexplained. A radio team found a strong, narrow signal on a printout. The event happened on August 15, 1977. A scientist wrote an exclamation on the paper. The team pointed telescopes again and again at the same place. They found no repeat. The signal stayed unexplained. Since that time, astronomers found many brief radio bursts. Some come from far away. Some come from objects that show repeat bursts. Some bursts come in narrow lines. Some come in wide bands. Scientists study each burst for its timing, its spectrum, its polarization, and its position on the sky. Each property gives a clue. Polarization tells how the electric field of the wave is oriented. Strong magnetic fields can change the polarization. If a burst is highly polarized, the source may sit in a strong magnetic environment. Measuring polarization gives a clue to the physics near the source. Localization is the task of finding the exact place in the sky. Some instruments give a wide patch of sky where the signal might come from. Other arrays of telescopes can find the place much more precisely. A precise place can link the burst to a galaxy, to a star, or to a small region. That link is very powerful. When a strange signal appears, teams follow a list of checks. The first check is the instrument. They inspect the telescope and the detector. They check logs. They look for sudden changes in the system. They check for faulty cables. They check the clock that stamps the time on the data. They test the electronics with known signals. A fault in the instrument can make a false event. The second check is local interference. Teams look for known human transmitters in the sky at that time. They check for radar sweeps, airline radios, satellite downlinks, and local transmitters. They check whether any devices at the observatory may have emitted the signal. A small microwave oven or a lab instrument can create a short burst that looks like a cosmic signal. Some false events show up in many beams of a radio telescope at once. A real celestial source usually appears in only one beam or in a pattern across beams that matches the beam shape. If the event is the same in all beams, it likely came from near the telescope. That test helped solve many false alarms. The third check is the data itself. Scientists reprocess the raw data. They run it through different software. They look for processing artifacts. Automatic filters can create spurious signals. A sharp filter edge or a threshold test may make a false spike. Reprocessing can show whether the event survives different methods. The fourth check is other instruments. Teams ask other telescopes to look at the same place. If another radio telescope sees the same event at the same time, the case is stronger. If a telescope that sees optical light reports a flash at the same time and place, this gives more support. X-ray and infrared cameras can add extra clues. A multi-wavelength signal is much harder to fake. The fifth check is the archive. Scientists search old data. They ask whether the signal appeared earlier and was missed. Many discoveries come from old files that are re-examined with new tools. If past data show similar events at the same place, the source may be repeating. The sixth check is the environment between the source and Earth. For radio bursts, the dispersion number gives the total free electron content. Scientists compare this number to models of the Milky Way. If the dispersion is larger than what the galaxy can give along that line of sight, the source is likely extragalactic. This helps to set the distance scale. The further a source is, the more energy it must release to appear bright. If a strange signal is narrow in frequency, scientists test whether natural masers or spectral lines can explain it. Some molecules in space make narrow emission lines. Water vapor and hydroxyl are examples. These lines appear at well-known frequencies. If the frequency of the signal matches a molecular line, it may be a natural maser. Some unusual signals show a sweep in frequency that does not match simple dispersion. Those sweeps may come from motion. If the source moves quickly, the frequency it emits can shift in time. Gas flows, orbital motion, or rotation can change the emitted frequency. Scientists model such motions to see if they fit the observed sweep. Another test is the pulse shape. Fast pulses can be simple and smooth. Other pulses show multiple peaks or fine structure on very short time scales. Very fine structure may imply a compact source, meaning the emitting region is small in size. Small size suggests high energy density and possibly exotic physics. Human-made signals can mimic many properties. aircraft and satellites move. Their signals can vary in frequency and time. Power lines can produce pulses when they arc. A clock in a piece of electronics can make periodic tones. Observatories keep lists of known local sources. They check these lists when a strange event appears. The history of transient studies shows many cautionary tales. Some events that seemed extraterrestrial were later traced to human causes. One well-known class of local events affected one radio observatory. The events looked like cosmic bursts at first. Later tests showed they came from a device operated near the telescope. This taught teams to be careful about local sources. Software can also cause false signals. Data pipelines pass raw files through many steps. Each step can introduce or remove features. A smoothing step can turn noise into a peak. An excision step that removes interference can leave gaps that the analysis treats as a spike. Teams test their pipelines with fake signals to make sure they do not invent events. Statistical tests help to judge how likely a signal is real. Scientists measure the signal-to-noise ratio. That is the strength of the signal compared to the background noise. They also count how many independent trials they ran. If a search looked at many times and many frequencies, the chance of a random noise spike is higher. Teams use known statistical methods to set thresholds that control the rate of false alarms. A key practice is confirmation by independent instruments and teams. If a different team finds the same event in their own data, the chance of a mistake drops. Independent confirmation is the strongest test for a real signal. Even after all checks, some events remain unexplained. Scientists then publish the data and the tests they ran. They ask the wider community to inspect the files. New ideas and new analyses may find an explanation. Openness speeds the process of finding the true cause. When a signal is unexplained, the scientific tone shifts from "this might be" to "we do not yet know." Teams avoid strong claims. They say what they tested and what they did not test. They highlight uncertainties. This careful communication helps avoid misleading the public. One class of unexplained events is short radio bursts with very high brightness. Some of these bursts arrive with a dispersion that implies they came from great distance. If true, these bursts must release a large amount of energy in a very short time. That fact drives many studies. Scientists test many models from natural physics to check whether any known process can produce such bursts. Another class is bursts that repeat irregularly. Repeaters give more data to study. Scientists can measure the distribution of burst times and energies. They can test whether the bursts come from a single source region. Some repeating sources show complex behavior. Some show periods of high activity followed by long quiet times. The pattern gives clues to the underlying physics. A further complexity is that some bursts show fine time structure down to microseconds or less. Detecting such fine detail requires fast instruments and careful calibration. These tiny features can carry key information about the source and the path the signal took. When scientists cannot explain a signal by known natural sources, they must also consider artificial origin. Artificial sources can be local or they can be sent from space. The idea of a transmitter moved to space raises many questions. A real test must carefully separate natural from artificial causes. If an artificial transmitter in space is possible, then the signal may show traits of communication. Repetition with a clear pattern is one sign. Narrowband tones and precise frequency control are another sign. A signal that sweeps in a strict coded way could also hint at information content. Scientists look for any sign of structure that would point to designed signals. At the same time, Natural processes can produce structured signals. Masers show narrow lines. Pulsars show precise periods. Magnetars show strong bursts with complex time structure. The line between natural structure and artificial code can be subtle. Careful analysis is needed. Because claims of artificial origin are strong, the standards of proof must be high. Teams use long lists of tests. They require independent confirmation. They require replication of results. They require that no plausible natural or local cause can explain the data. Scientists keep a record of many odd events and the results of the checks. Some events turn out to be human once the source is found. Some remain open. The open events become the subject of ongoing study. New instruments and new methods may resolve them later. Fast follow-up is important. If a burst is short and bright, telescopes must point quickly to the same spot to catch any afterglow. Afterglow in other bands can help identify the host. A host galaxy can tell the distance. Distance sets the energy scale. This helps decide which models can work. Clear records are crucial. Teams record the time and the exact coordinates. They save raw data and process data. They log the instrument settings. They save any notes about maintenance or activity at the observatory. These details help later teams reproduce the checks. Peer review and open data strengthen the process. When teams publish data and methods, others can test for errors. New ideas can be tried on the same files. This mutual testing is a key part of science. In some cases, new hardware or new observing strategies can resolve long-standing puzzles. Arrays of telescopes that work together can localize a burst to a small region. That small region can then be observed by optical and infrared telescopes. Spectra of the host can be taken. These steps can reveal the nature of the source. The path from an unexplained signal to an explanation can be long. It may require years of data. It may require instruments that did not exist when the first event was seen. Scientists save the data and return when new tools become available. A single unexplained event does not prove a new physics or a new civilization. It is a sign that more work is needed. The correct path is careful testing. The goal is to find the true cause with high confidence. If all natural and local causes are ruled out, scientists may include in their checks whether a small artificial device could cause the signal. A device in space could send narrow signals in radio. It could make short bursts. It could store data and send a burst rarely. To judge that possibility, teams must know what small devices can do and where they might hide. This is the next question scientists must study. To judge whether a small device could make an odd signal, scientists must know what small machines can do in space. Small machines can do many useful tasks. They can listen for radio waves. They can take pictures in visible light and in other bands. They can sample dust and gas. They can test the chemicals in a sample. They can store data for a long time. They can send short radio messages. They can move on small paths. They can also stay in one place and watch. Each task needs parts that fit inside a small body. The choice of parts sets what the machine can do and how long it can work. A listening device can have a radio receiver. The receiver can scan a range of frequencies. It can record the strength of a signal at each frequency and the time when the signal arrived. A simple receiver uses an antenna and an electronic unit that converts the radio waves to numbers. Those numbers can be stored in memory. If the memory is full, the device can send a short report. The report can say the time, the frequency, and how strong the signal was. The device can be programmed to ignore human-made frequencies. It can be tuned to store only signals that meet certain rules. Those rules can be narrow and strict to save memory and power. A camera can record images in visible light. A camera has a lens or a small mirror and a detector. The detector turns light into an electronic signal. The camera can use a filter to record specific colors. Infrared detectors measure heat. A small infrared sensor can record warm spots on a surface or in a cloud. Ultraviolet detectors can record light at shorter wavelengths than visible light. Some detectors work at X-ray or gamma-ray energies. Those detectors need special materials. They are compact enough to ride on a small probe in some designs. Each detector type gives a different view of the target and of the surrounding space. A small laboratory can test dust and gas. Micro-instruments can trap a tiny grain and heat it. When the grain heats, gases can escape. The gases pass over a sensor that measures their composition. A tiny mass spectrometer can give a list of the atoms and molecules present. Chemical sensors can look for water, oxygen, carbon, and other simple chemicals. These instruments use little mass and little power. They do not need a full-sized laboratory. A device can use a set of simple mechanical tools. It can carry a drill or a scoop that collects a small sample. It can use a small arm to place a sample into a sensor. Motor-driven parts need careful design to avoid wear. Bearings and seals must work in vacuum. Lubricants behave differently in space. Engineers choose parts that survive the cold and the radiation. The design can favor few moving parts to reduce failure points. Storing data on board is essential. A device can use solid-state memory to save numbers and images. Memory can keep data for many years if the electronics are radiation-hardened. Some devices store compressed data. Compression reduces the size of files. The device can save only the key features of a recording. It can keep a short raw segment and a reduced summary for routine use. When a rare event happens, the device can save longer raw files for later transmission. Communication can take many forms. A device can send a narrow radio beam. A narrow beam uses an antenna or a small dish to focus the signal to a target. A focused beam uses less power to reach a receiver at a chosen place. A device can send short bursts at planned times. It can also store data and send only when a relay satellite passes overhead. Low-duty transmissions save energy and reduce the chance of detection. A device can use low-rate telemetry. It can send a few numbers each contact. The numbers can report the status of the device and a short summary of its recent recordings. In this mode, the device conserves power and antenna time. When a strong event occurs, the device can switch to a high-rate mode and send more data. Error correction and coding help the data arrive intact. The device can use simple codes that let the receiver fix some lost bits. The device can send the same packet multiple times in case of loss. It can use handshake protocols that wait for an acknowledgement. For long-distance links, the device can use store and forward. It sends data to a relay that later forwards the data to a central receiver. Power defines the range of actions a small device can do. A device can carry small solar panels. Solar panels provide power while sunlight falls on them. In shadowed regions, solar panels do not provide energy. A device can carry batteries to store power. Batteries supply energy during short bursts and during periods of darkness. Many small devices use efficient electronics to stretch their energy budget. Some devices can use radioisotope power. A radioisotope thermoelectric generator converts heat from the decay of a small radioactive source into electricity. This source can provide steady power for many years. That steady power allows continuous monitoring and slow data transmission over long times. Radioisotope sources must be handled with strict safety rules when they are built and launched. Propulsion and attitude control let a device move and point. Small thrusters provide short pushes that change the speed and direction. Reaction wheels can rotate a device to aim an antenna or a camera. Small cold gas jets can push the device and remove momentum. Electric propulsion systems can provide a small continuous thrust over long times. That thrust can move the device from one orbit to another with little fuel use. Each propulsion method needs propellant or an energy source and adds mass to the device. Mobility can be local. A device can hop on a small body. A hopping motor can lift the device and set it down at a new place. Mobility helps to sample different locations on a surface. Mobility can be limited by terrain and by the energy available. Thermal control is necessary. Electronics work best in a narrow temperature range. Heaters and radiators keep the device within operating temperatures. Thermal paint and insulation help. The device can open a radiator to dump heat or close it to retain heat. In shadowed regions, the device needs heaters to stay warm. In bright sunlight, the device needs radiators to avoid overheating. Thermal control affects the detectability of the device in the infrared band. Radiation affects electronics and sensors. High-energy particles can flip bits in memory and can damage detectors. Devices can use radiation hardparts and shielding. They can also use redundancy. Critical functions can have two independent units. If one unit fails, the other can take over. Redundancy increases mass but improves the chance of long life. Autonomy makes small devices useful at times when no one can talk to them. A device can follow a program of actions. It can wake at a set time and record for a fixed period. It can also act on triggers. A trigger can be a threshold in sensor readings. For example, a radio receiver can wake the device when a signal above a set strength appears. An optical sensor can wake the device when a flash passes a threshold. Autonomy reduces the need for a constant link to a human operator. Software controls the sequence of actions. The software can do simple rules, or it can include complex decision-making. Small devices can run algorithms that detect patterns and classify signals. They can flag events that meet a set of criteria. They can decide which data to send and which to archive. Software can also manage power by reducing activity during low power states. Upgrades to software can occur if the device has a communication link that allows uploads. The device can receive a new program and run it. Secure update methods prevent corrupt or harmful code. Encryption and authentication help ensure that only authorized commands change the software. A set of small devices can work as a network. One device can act as a node that receives data from others and forwards it to a central receiver. Relay nodes can extend the reach of a small transmitter. Devices can form a chain of links that pass data over long distances, while each link uses modest power. Swarm behavior can divide tasks among units. Some devices can focus on listening. Others can focus on imaging or on sampling. Task specialization reduces the mass and power needed for each unit. A network can schedule who talks and when. That schedule avoids collisions on shared frequencies. Cooperation can include synchronized measurements. A set of devices can observe the same event at the same time from different positions. That multi-point data helps measure the direction and polarization and timing of a signal. Timing differences between nodes help locate a source. Precise clocks are necessary. Small devices can carry stable oscillators to mark time over many hours. Some designs include small atomic clocks for high precision. Stealthy design choices affect how easy a device is to detect. A device can reduce its optical reflectance to avoid bright reflections. It can operate with low thermal waste to avoid infrared detection. It can use highly directional radio beams so that most of the radio energy goes to a chosen receiver. It can use brief transmissions that are hard to catch in a short observation window. Each choice reduces detectability but also sets limits on power and on what the device can do. Self-maintenance increases lifetime. A device can monitor its own health. It can switch to a backup unit when a component fails. It can reclock a damaged oscillator by referencing a stable external signal. Some devices can move to a favorable orientation to warm a cold unit or to cool an overheated unit. Spare parts can be carried for small repairs. Self-replication is a complex capability. Building new units from local material needs tools, energy, and raw material. A simple replication process can make a copy of a small device by assembling prefabricated parts carried in a host. A full replication process would need mining and manufacturing systems on site. That level of complexity is heavy and demands energy and mass. It is a high bar for small devices. Material choice affects longevity and signature. Metals conduct heat and reflect light. Carbon-based composites can have low reflectance and low thermal emission. Coatings can be applied to change reflectivity and thermal emissivity. Surfaces can be roughened to reduce strong specular reflections. The surface treatment must survive micrometeoroid impacts and radiation over long times. Small devices face limits. Energy is finite. Memory is finite. Antenna size limits the radio beam shape and the transmission efficiency. Detectors have limited sensitivity. Moving uses energy and propellant is limited. Designers trade off among these limits. They choose the mix of sensors and the mission plan to get the most useful data for a given mass and power budget. The limits lead designers to use careful planning. They set thresholds that trigger detailed recording only when events meet specific rules. They plan contacts with relay nodes or with ground stations to move data when the alignment is right. They plan long idle times in which the device sleeps to save energy until a key event or a scheduled time. Small devices can be built to last for many years. Long life requires robust parts, conservative operating modes, and energy sources that supply a steady baseline. Radioisotope power sources, large batteries, and reliable solar panels can support a long mission. Long life also requires keeping moving parts to a minimum and providing redundancy for critical systems. Small devices can be placed where human surveys are thin. They can sit on small rocks or near stable points in space. They can remain hidden in shadowed regions. They can watch for long times and record rare events. The combination of listening, imaging, sampling, storing, and selective transmitting gives these devices a wide set of capabilities. Knowing what small devices can do helps to set the tests for strange signals. If a signal could be sent by a small device, people need to consider the signals that such devices can make and the places they can be. The next step is to learn how a device could be designed to avoid easy detection. That step looks at choices of shape, surface, and how a device uses its energy and its radio links. Design choices change how easy a small probe is to find. A maker can choose shape, surface, power, and radio use. Each choice changes what the probe gives off. Each choice also changes what the probe can do. Here are the main ways a small device can avoid easy detection. First, the device can reduce how much visible light it reflects. Telescopes that see visible light look for reflected sunlight. A device can use dark coatings that absorb light. The coatings can make the surface matte or rough. A rough surface scatters light in many directions. A matte finish does not make bright glints. Both reduce bright spots that a telescope can pick up. The device can also point its least reflective face toward strong light. That choice lowers the amount of light that returns to a distant observer. Second, the device can reduce its heat signature. Infrared detectors see heat. Any electric system, any radio transmitter, and any battery gives off heat. A design can move that heat inside the body and release it slowly. It can use thermal insulation to keep heat from reaching an external surface quickly. It can use radiators that send heat into a shadowed area where few instruments look. A device can operate in a low power mode most of the time. Low power reduces waste heat. A device can store energy and release that energy in short bursts. That short release can carry data, but the average infrared emission remains low. Third, the radio transmission can be narrow and brief. A simple transmitter that sends a wide cone of radio energy is easy to detect. A more focused transmitter uses an antenna that points a narrow beam at a chosen receiver. A narrow beam sends most energy toward the receiver and little energy elsewhere. If the beam never points to Earth observers never hear it. If the device sends only short bursts at rare times, the chance that a telescope is listening at the same moment is small. The device can also choose frequencies where human radio use is low. It can avoid busy bands and use quiet bands. The device can use precise timing for transmissions, so the receiver knows when to listen. That approach saves power and reduces the time the device emits. Fourth, the device can reduce its radar echo. Radar works by sending radio pulses and measuring the return. A device can lower the radio reflection by using materials that absorb radio waves. It can shape the surface so that the radar energy does not bounce back to the sender. It can place its reflective surfaces at angles that send most radar energy away from likely radar sources. A small size also reduces the radar cross-section. A small object returns much less energy than a large one. Designers can add coatings that trap radar energy or convert it to heat that they then release slowly in a way that blends with the background. Fifth, the device can hide in shadow. A body in deep shadow does not reflect much sunlight. An instrument placed behind a large rock or in a crater can be in permanent or long-lived shadow. In that position, it avoids bright optical detection and it reduces solar heating. A shadowed place changes the power options. Solar panels do not work well in shadow. The device must carry other sources or store energy. That trade-off can make a device last longer in a passive mode and still remain quiet. Sixth, the device can match natural materials. A surface that looks like rock or dust will not stand out in optical or infrared surveys. If the surface has the same spectrum as natural rock or regolith, it will not show unusual spectral lines. The device can use coatings that mimic the color and the thermal properties of local materials. That choice can make the device blend in when scanned with cameras or spectrometers. It also makes it harder to find when the object sits on a rock or in dust. Seventh, the device can use minimal moving parts. Moving parts can give off heat and can make sounds or vibrations. In space, moving parts can also throw small debris. A device with few moving parts has fewer failures and a lower profile. If a moving part does fail, the device can go silent. No moving parts lowers the chance of detection from unexpected signals. Eighth, the device can use long-life power sources that are quiet. Solar panels give power when sunlight falls on them. Batteries give stored power for short time. A radioisotope thermoelectric generator gives steady power for a long time. That steady power comes with steady heat from decay. The device can design heat paths to hide that heat from broad view. The choice of power matters for how the device looks in infrared and for how often it can transmit. Ninth, the device can store data and send only summaries. If the device keeps full raw recordings locally and sends only short packets of summary data often, the transmissions are small. The device can send longer files only on rare scheduled contacts. If the device talks to a local relay, it can send its bulk data to that relay with low power. The relay can have a larger antenna for long-distance links. This structure keeps each small device quiet while letting the network move data when needed. 10th, the device can use a network of units. A group of small probes can split tasks. One unit can listen for signals, another unit can image a target, a third unit can carry a relay. If the listening unit detects an event, it can cue the relay to wake up and receive data. The relay can then send a stronger, focused transmission to a distant receiver. The network reduces the need for each unit to emit at high power. The network can also keep individual units idle most of the time. 11th, the device can have smart triggers. It can wake only when a sensor measures a threshold. A radio receiver can wake the system when a strong radio pulse appears. An optical sensor can wake the recorder when a bright flash occurs. A chemical sensor can wake the data logger when a certain gas is present. Smart triggers save power and lower the time the device is active. They also reduce the number of transmissions. 12th, the device can use tight frequency control and coding. A transmitter that holds an exact frequency is easier to find in spectrum scans than one that hops among many frequencies. A hopping transmitter may be seen as noise. A coded transmitter can send data in a form that only a known receiver can decode. If the code is unknown to Earth observers, the emission may look unremarkable and be ignored. The device can choose codes and protocols that are uncommon or that match local needs. 13th, the device can limit its antenna size to reduce visibility. A small antenna has a wide beam unless the frequency is high. A wide beam spreads energy and makes a transmitter easier to detect at many directions. To keep the beam narrow without a big antenna, the device can use higher frequency transmissions. High-frequency signals attenuate more in some media. The device must balance frequency choice with power needs and with the receiver capabilities. 14th, the device can use directional shielding. A device that has a shield on one side can aim that shield toward bright sources or toward frequent scans. The shield can block thermal radiation or reflected light. The device can open the shield only when needed. The shield can be made of materials that keep heat inside for a time. The device can then vent heat at times when observers are unlikely to watch. 15th, the device can accept a lower data rate. Slow transmissions need less power. Slow transmissions take more time for the receiver, but they reduce the chance of detection by a casual scan. The device can spread data across many short windows. Each window may be below normal detection thresholds. Over time, the receiver can build the full message from many small pieces. 16th, the device can set a strict observation plan. It can listen to only a few chosen signals. It can ignore broadband noise to save memory. It can sample at lower rates for long-term monitoring and then sample at high rate when the trigger fires. A planned observing regime keeps average activity low. 17th, the device can be shaped to reduce specular reflection. Flatter or faceted surfaces can direct sunlight away from common viewing angles. A shape with many small facets scatters light broadly. A shape with a gently curved surface can send reflected light to angles where telescopes usually do not point. The shape must also support antennas and sensors, so the designer must balance the needs of detection avoidance with the needs of function. 18th, the device can hide under a layer of natural dust or regolith. A shallow burial hides most of the body. A thin cover can reduce visible and thermal signatures strongly. Buried devices are hard to find with simple imaging. Radar can probe below the surface, but the radar return may blend with the surrounding material if the device matches the material properties. Burial requires tools or an initial method to place the device under the surface. 19th, the device can exploit orbital and positional choices. Placing the device at a point that stays in a stable location relative to a planet or star can reduce the need for station keeping. A stable point reduces the need for active propulsion, which reduces emissions. Fixed positions can also make careful pointing of radio beams easier. Choosing a location with high background brightness can mask the presence of a small, dark object. Choosing a quiet radio environment can reduce the need to use strong transmissions. 20th, designers must accept limits and trade-offs. Low emission makes many tasks harder. A device that hides in shadow cannot use solar power at that time. A device that uses small antennas must accept short range. A device that stores data must risk data loss if it cannot find a relay. Each choice adds a cost in capability. Makers must decide which capabilities are essential and which can be reduced. 21st, stealth choices can make a device fragile to some hazards. Insulation that traps heat can fail in strong sunlight events. Low power modes reduce the ability to respond to damage. Complex coatings may degrade under radiation or micrometeoroid impacts. Designers must consider long-term survival and maintenance. 22nd, stealth can be balanced with redundancy and repair. A device can have duplicate critical components that remain cold and idle until needed. It can include spare memory that takes over if the main memory corrupts. It can carry small robotic repair tools that can restore a failed sensor. Repairs use energy and material. Designers must weigh the added mass and complexity. 23rd, some choices lower the chance of accidental discovery. A device that never transmits at wide angles is less likely to be heard by accident. A device that does not reflect strong light is less likely to be imaged by surveys. A device that does not have moving parts avoids sudden flashes and sounds that may attract attention. Careful behavior reduces accidental signatures. 24th, some stealth choices increase the chance of detection in other ways. A device that uses a radioisotope power source gives off heat all the time. That heat can be found by infrared surveys if the emission pattern is not well hidden. A device that uses high-frequency radio to narrow the beam may be seen by instruments that monitor that band carefully. A buried device may be found by ground-penetrating radar or by a probe that disturbs the surface. Designers must weigh all detection modes. 25th, a device can be built to test its environment for signs of being scanned. It can have sensors that detect radio or radar energy aimed at it. When it senses a scan, it can go quiet, change orientation, or move deeper into shadow. Such behavior reduces the chance that a scanning pass will find it. The device must react quickly and must avoid false triggers that make it hide unnecessarily. 26th, the maker of a device may plan for a long, quiet life. The device can be designed to run for many years on low power and to transmit only rare status checks. It can store the most valuable data for a future relay. Long-life design stresses reliability, simple modes of operation, and materials that resist radiation. 27th, a device can use small reflectors or surfaces to direct a faint signal to a known receiver. Small reflectors can be aimed precisely so that a weak transmitter still reaches the receiver. The reflectors must be stable in shape and must avoid stray reflections. The use of reflectors reduces the need for a large active antenna. 28th, the device can make its surface appear physically similar to the local rocks. If the maker expects that no human will inspect the surface closely, the easiest approach is to match the optical and thermal behavior of nearby material. That choice reduces the chance that routine surveys mark the object as suspect. 29th, a device that aims to avoid detection must still be able to do useful work. It must balance stealth and function. A listening device must have a good antenna to hear signals. An imaging device must have a lens of some size for resolution. A sample analyzer must carry sensors that require power. The maker must choose the most important goals and design for them within the stealth plan. Finding a small quiet device is hard when it is designed to be quiet. Yet every design choice leaves traces. Low reflectance, low heat, narrow radio beams, shadowed positions, burial, and matching local materials all make detection more difficult. At the same time, each choice changes what the device can do and how it can communicate. Knowing these design choices points to the next question. If a device can hide in these ways, then where could such a device be placed near our planet so that it uses these options and remains hidden? A device that wants to hide must choose a place near our planet to sit and wait. Many places around Earth can help a small device stay quiet. Each place gives the device different chances to hide and different needs to work. The choice of place sets how the device uses light, heat, and radio. It also sets how easy people will find it. Low orbits close to Earth are one option. In these orbits, the device passes over the ground fast. Telescopes on Earth and radar systems watch many parts of low orbit. That makes finding objects easier there. Still, many small pieces of debris orbit close to Earth. A small and dark device can blend with that clutter. Low orbits have the benefit that solar panels can often get light. That helps devices that need solar power, but the air at low altitude causes drag over time. A device must have a way to keep its speed or it will fall back to Earth. That need makes long life in low orbit harder unless the device has fuel. Very high orbits far from Earth are another place. Far orbits put the device where ground-based radar is weak. The device moves more slowly as seen from Earth. A device in a far orbit can sit in a place where old surveys do not look often. Far orbits need more power to send data to Earth. A device in a far orbit may use a focused radio beam to reach a receiver. A focused beam reduces the power needed. Still, being far means the device must carry stronger transmitters or wait for a relay to pass by. Geostationary orbits sit over the equator and keep the same place above the ground. Many communication satellites use that zone. The zone has many objects to hide among. People monitor the zone because it supports many services. A small, dark object in that orbit can hide in the crowd if it moves little, but satellites in that zone must often be large enough to be useful. A very small device that tries to hide there may be noticed by the many systems that watch communications satellites. Graveyard orbits and special high lanes are places beyond the common working zone of satellites. Some satellites go to a higher lane at the end of life. These lanes are less watched. A device that sits in a quiet high lane can stay far from regular surveys. The farther out the lane, the harder it can be for ground radars to return a strong echo. But a device there must still plan how to get power and how to send data to Earth. Orbits that are very elliptical can help a device stay quiet. In these orbits, the device may spend long times at far distance and short times near Earth. The near passes can be short and rare. If the device only acts during the far part of the orbit, many surveys near Earth will not see it. But these orbits are complex to keep. The device must use some control to keep its path safe. Stable points in the space between Earth and the Sun are special places. These are spots where the pull of gravity from Earth and from the Sun balance. A small object can sit in such a spot and not drift away quickly. These points exist ahead of and behind Earth along its path around the Sun. They can hold dust and small rocks. A device placed at one of these points can stay for a long time with little fuel use. The points do not face Earth directly. That can make communication harder. A device at such a point may need a relay to talk to Earth. Surveys from Earth may not point often to those spots. That makes detection harder. Points near the Moon can also hold small objects. There are spots around the Moon where a probe can stay with little fuel. These spots can be behind the Moon or off to the sides. A device placed there can watch the space near the moon or watch the Earth. Some spots near the moon sit in stable dust clouds. Those clouds are faint and hard to image. A device in a dust cloud can blend into the background. The surface of the moon offers many hiding places. The far side of the moon faces away from Earth. That side does not have direct radio contact with Earth. A device on the far side can avoid being heard from Earth unless it has a relay. That helps a device stay quiet. The far side has many craters. A device can sit on the floor of a crater and be in shadow at times. A shadowed spot reduces visible and infrared signatures. The poles of the moon have deep craters that stay dark for long times. Cold traps in those craters keep low temperatures. That limits the use of solar power. A device in a polar shadow can be hard to find with optical surveys. The near side of the moon also can hide devices. People point telescopes at the near side more often. Still, large parts of the near side are rough and filled with boulders. A small, dark device can sit close to a rock and not stand out. The near side is easier for a device to send radio messages if it wants to talk to Earth directly. It may also be easier for humans to send a probe that inspects the spot. A device on the near side must weigh the ease of communication against the chance to be imaged. Some small rocks pass close to Earth for a while and then move away. These passing rocks can be tiny and hard to see. A device that lands on such a rock can hitch a ride near Earth for a time. If the rock moves slowly relative to Earth, the device has more chances to observe. If the rock moves fast, it may be near Earth only for a short time. Temporary capture can trap a small rock in an orbit around Earth for months or years. Such temporary captured rocks are called mini-moons. A device on a mini-moon can stay near Earth without needing to carry much fuel. The problem is that mini-moons are small and faint. They are hard to find and to study from Earth. Some objects share an orbit with Earth. They move with Earth around the Sun. These co-orbital objects can stay near Earth for long times. They can follow paths that keep them near the planet. A device placed on a co-orbital body can remain near Earth without needing much fuel. Such bodies are faint and they move slowly in the sky. Surveys may not focus on them often. That makes them a possible hideout. Dust rings and clouds in the plane of the solar system also exist. The plane around the Sun where most planets orbit can hold dust and small particles. A device within a cloud or inside a dust ring can be hard to distinguish from the background dust in visible and infrared bands. The dust blurs the signature of a small object. Radar can still probe some dust clouds, but the return may be weak. A device in a dust cloud can be hard to pick out by shape or by spectrum. Space near Earth contains many human-made items. Debris from rockets and old satellites fills some orbits. A device can hide among that debris. In low orbit, there are many small pieces that are hard to track. A dark device of similar size can go unnoticed. Being near debris has risks. Collisions are more likely. Collisions can damage a device. The maker must weigh the benefit of hiding against the danger of impact. Dust and regolith on the moon and on asteroids provide a hiding method. A device can be buried under a thin layer of dust. Even a shallow burial can hide a device from many optical surveys. Thermal signatures can also be reduced if the device sits under material. Radar can sometimes see under a shallow cover. The radar return depends on the contrast between the device and the surrounding material. If the device matches the material well, radar will not easily pick it out. Craters and caves can hide a device. A device placed within a cavity can avoid direct sunlight and reduce its reflective signal. Caves can hold a device in thermal balance. The cave walls can hide heat emissions. Entry to caves and deep hollows can be hard for human probes to reach. A device that sits inside a cave or deep crack is less likely to be seen by ordinary imaging. Tiny moons of other planets are farther away, but they can be a place for some devices. For a device to sit on a moon of another planet, it must travel farther and require more energy. That travel cost may be high. Still, such moons have low gravity and low interference. A device on a small moon near the inner planets may still watch the inner system. It will be far from Earth, so direct detection from Earth becomes harder. The plane of Earth's orbit around the Sun is populated by many objects. Some of these are small and faint. A device that sits in the main plane will be layered among many natural sources. Surveys that sweep the plane may overlook a faint, dark object in a crowded field. The plane holds many moving parts and many sources of noise for telescopes. Polar shadowed regions on the Moon and on some asteroids are very cold. A device in a cold shadow can keep its heat inside and release it slowly. That lowers its infrared signature. Cold regions also lock electronics into low power modes. The device must plan for limited power. Radioisotope power or stored energy can supply long life in such places. A device that uses a radioisotope generator must hide the steady heat output. That heat can be a signature to sensors that look in the infrared. Stable orbits near Earth can be used for long-time watching. A device at a stable spot does not need to burn much fuel to stay. It can sit for decades. That long life helps the device observe rare events. It also lets the device wait for a time when it is safe to send data. But stable spots can be targets for human missions. If people examine such spots, devices there may be found. Positions that move slowly relative to the Sun make a device blend with the natural motion. If a device moves with the flow of natural bodies, it is less likely to stand out in motion searches. Surveys look for fast-moving objects or for objects that cross the sky quickly. A device moving with the general flow will be harder to separate from the background. Shadowed positions behind large objects are useful. A device that hides behind the Moon or behind a large planet is invisible from the side that faces the observer. The body of the Moon or of the planet blocks light and radio from the device. That block helps the device remain quiet. But hiding behind a large body also cuts the device off from direct sightlines to Earth. The device will need a relay or must be able to wait for the right geometry to send signals. Places that are rarely observed by surveys are attractive. Some regions of the sky get little attention. Ground telescopes avoid times of bad weather. Space telescopes point away for some missions. A device in a rarely seen region can sit for a long time. Surveys that cover the whole sky will eventually reach most places, but the coverage can be sparse in time. Rare events can be missed if the device sends a brief burst only when no one is looking. Small objects on slow orbits can hide near the Sun from Earth view. Observing close to the Sun is hard because the bright light overwhelms faint objects near it. Instruments often avoid the region near the Sun. A device that sits near the Sun as seen from Earth can be hard to see, but that place is hot and has a strong radiation environment. The device must be built to survive heat and particles. Stable dust clouds at points ahead and behind Earth may hold small objects. These points in Earth's path can gather dust. A device placed where dust collects can gain a natural cover. The dust may also slow down active searches. The dust spreads a device's thermal or optical signature over a larger area. A device may use a moving small rock as camouflage. It may land on a rock that spins slowly and change its orientation so it stays in shadow. The rock's motion can make the device's signature vary in time and thus confuse detection. A device on a rock can also move when the rock approaches Earth. Mobility of the host rock is a factor in planning detection. If the device wants to monitor Earth, it may pick a place that sees the planet. Near side orbit, low orbit passes or high orbits with Earth view let the device watch. If the device wants to stay unseen, it may avoid direct lines to Earth and use relays or delayed transmissions. That choice changes how a device sends its data. The ease of human search varies by place. Low orbit and geostationary zone are well surveyed. Many observatories and radar systems watch those zones. The Moon's surface has been imaged, but much of it is rough and not mapped at very high resolution for all spots. Small rocks and dust clouds are often faint and missed. Stable points and far orbits are less well mapped. They get fewer observations. Shadowed caves and buried devices are hard to see from outside. A device placed near Earth must balance power, communications, and the risk of discovery. Some places help with power but are more visible. Other places help to hide but require other ways to get energy. Each place forces trade-offs. Finding a hidden device requires different searches for each place. Ground radar is strong at close ranges in some orbits. Optical telescopes can image bright reflections. Infrared sensors can find heat. Space-based telescopes can look where ground telescopes cannot. A buried device or one in deep shadow can hide from all of these sensors unless a probe visits the spot. A small device can use many of the hiding options at once. It can sit at a stable point in shadowed dust. It can be coated to match local materials. It can use rare short radio bursts to a dedicated relay. It can wait long times between transmissions. Each layer of hiding makes detection harder. Knowing where devices could hide helps to plan the searches. Different places need different tools and different observing times. Some places can be checked with short surveys. Other places demand long and patient monitoring. Each place is a small world with its own limits and its own chances for discovery. Searching for small, hidden devices is not easy. Many places near Earth have features that help hide them. The search must be broad and steady. It must use many sensors and many methods to cover the variety of possible hiding spots. The next step is to look at what current surveys and instruments can miss in each of these places. Knowing where a device could hide helps us see what our instruments might miss. Many searches do not find small objects. The reasons are many. They come from limits of the instruments. They come from how we process data. They come from choices in observing plans. They come from the environment near Earth. This chapter lists the main limits and explains them in simple words. Optical telescopes look for light that is reflected or emitted. They have limits in brightness. A telescope can detect an object only if the object is bright enough during the exposure. If the object is faint most of the time, the telescope may not see it. The surface reflectance matters. A very dark surface returns little light. Small size reduces the reflected light. A small dark object can be fainter than the survey limit. Exposure time matters. Many survey telescopes take short exposures to cover a large area of sky. Short exposures catch bright objects. They can miss faint objects. Deep surveys take long exposures on a small patch of sky. They find faint objects in that patch. They do not cover the whole sky. A small object that moves or that sits in a rarely observed patch may be missed. Pixel size and resolution matter. A small object can fall inside a pixel that also holds a star or dust. If the object does not change the pixel brightness enough, it will not be detected. Image processing may remove small differences as noise. Many surveys subtract a reference image to find changes. Subtraction works well for steady fields. It can fail in crowded areas or near bright objects. Artifacts from subtraction can hide or erase faint-moving objects. Motion can hide objects. A fast-moving object can trail in an exposure. The light of the object spreads over many pixels. The peak brightness can drop. Objects that move between frames may not be linked by the moving object pipeline. The pipeline often requires seeing the object in 2 or more frames to form a track. If the object appears in only one frame and then is gone, it may not be recognized. Sky glare reduces sensitivity. The region near the sun is very bright. Observations there are difficult. Many surveys avoid the region close to the sun. A device that stays near the sun as seen from Earth can stay unseen. The moon can also cause glare and hide faint objects near it. Crowded fields are hard. Toward the plane of the solar system there are many stars and many small bodies. In crowded fields, a faint object can be lost in the background. Surveys often have fewer useful results in crowded regions. This reduces the chance to find a small device that sits in a busy zone. Optical surveys have a cadence. Cadence is how often a spot is observed. A rare brief event can happen when no telescope points there. If a device flashes for a short time, it may be missed unless a telescope was watching. Many searches rely on planned cadence. Rare events need serendipity or wide continuous monitoring. Infrared telescopes look for heat. They detect objects that give off thermal energy. The instrument sensitivity depends on the background sky. The sky in infrared is bright from dust and from the atmosphere for ground telescopes. Space infrared telescopes have better sensitivity. Still, a very cold device gives off little infrared. A device that stays cold in shadow or that radiates heat slowly can evade infrared detection. Thermal inertia matters. Small objects heat and cool quickly. In sunlight they warm, in shadow they cool. A device that uses insulation can hide its heat. If it releases heat only rarely, the averaged infrared signal can be below detection. Infrared surveys often scan the sky and set patterns. A single brief thermal pulse can go unseen. Radar probes a target by sending radio pulses and measuring the return. Radar detection needs reflected energy above a threshold. The radar cross-section depends on size, shape, and material. A small object with low reflectance can return very little energy. Ground-based radar searches focus on near-Earth objects of a minimum size. Objects below that size give returns too weak to detect at typical ranges. Radar beam time is limited. Pointing radar at large volumes of sky takes time and energy. Radar surveys often target known objects or predicted close approaches. A device that sits in a region not targeted by radar can remain unseen. High-power radar can detect small objects at moderate ranges. High-power radar is expensive and it is not used continuously. Radio telescopes listen for radio waves. They have many limits. The radio frequency range is wide. No one instrument covers all frequencies. Receivers cover specific bands. A transmitter on a frequency outside common bands will not be seen by most surveys. Radio frequency interference is a major problem. Earth is full of human radio signals. Radio surveys must filter or remove interference. Strong local signals can blind a radio receiver. Weak signals can be masked by the noise of human transmissions. Many searches apply filters that remove narrowband tones and periodic signals. That removal can erase a real narrowband signal if it resembles human interference. Time resolution is important. Fast bursts need high sampling rates. If a radio telescope samples at a slow rate or integrates over long time windows, a fast burst that lasts 1 millisecond will be smeared out and may be invisible. Some instruments keep raw baseband data in short buffers and save only when a trigger fires. If the trigger threshold is too high, or if the trigger criteria do not match the burst, the raw data will be lost. Dedispersion is a processing step for radio bursts. A dispersing medium delays low frequencies more than high frequencies. To find bursts, software tries many dispersion values. That requires computing power. To keep computing needs in check, searches limit the range and the resolution of dispersion trials. A burst with an extreme dispersion value or an unusual frequency sweep may be missed. Beam patterns matter. Single-dish telescopes have a main beam and side lobes. A strong signal in a side lobe can appear to come from a different place. Side lobe detections can be confused with local interference. Interferometers have complex beam shapes that change with frequency. Calibration errors can reduce sensitivity or produce spurious signals. Localization can be poor. Many radio bursts are detected with poor position accuracy. Without a precise position, optical and infrared follow-up is hard. Follow-up can fail if the error region is too large. This reduces the chance to find a counterpart in other bands. Dynamic range limits affect radio and optical instruments. A very bright source in the field can saturate detectors. Saturation reduces the ability to detect faint neighbors. Strong radio transmitters can create artifacts in the data. Those artifacts can hide faint real signals. Data volume is huge. Telescopes produce many terabytes of data per day. Storing all raw data is costly. Many facilities keep only processed data or short buffers of raw data. Long-term archives often hold reduced files. Rare events that need raw baseband files may be unrecoverable if those files were not saved. Storage limits force choices. Those choices can make rare short events disappear from the record. Processing pipelines discard data. To speed analysis, pipelines remove samples that look like interference or noise. Those steps reduce false alarms. They also risk removing real unusual signals that do not match expected patterns. Machine learning classifiers are used more often. They can reject events that are not in their training set. Novel signals may be labeled as noise and removed. Human review is limited. When millions of candidate events are flagged, experts must prioritize. Many events are never inspected in depth. Teams focus on the most promising or most familiar types. Unusual signals can remain unexamined or underreported. Survey design creates blind spots. All sky surveys are broad and shallow. Deep surveys are narrow. Time domain surveys focus on a few patches. Many regions are observed rarely. A device that stays in a rarely observed region will be missed. Instruments that avoid the sun direction create a blind zone near the sun. This zone is hard to search from Earth. Scheduling and operations limit coverage. Telescopes follow schedules. They cannot watch everything at once. Weather and daytime affect ground telescopes. Space telescopes have competing tasks. A device that emits at a time when instruments are busy or when ground telescopes are offline will be harder to catch. Calibration and maintenance create gaps. Instruments go offline for repairs or upgrades. Gaps in coverage create times when events may occur unobserved. An instrument that is being tuned can generate spurious signals. Those spurious signals may be labeled as instrument noise and not shared widely. Archival search methods have limits. Old data are reprocessed with new methods. Still, archives do not hold every data type forever. Intermediate products are often stored for long times. Raw data are often kept for shorter durations. If a reprocessing needs raw files that are gone, a past event cannot be rechecked. Statistical thresholds set detection limits. To avoid too many false positives, teams set strict thresholds. That reduces the number of weak detections. Many weak but real signals fall below the threshold. A balance must be made. Too low a threshold gives too many false alarms. Too high a threshold misses faint real events. Human-made noise changes over time. New satellite constellations increase radio and optical noise in the sky. The number of active satellites has grown. Their signals and reflections add to the background. Surveys that once had clean skies see more clutter now. Noise that rises slowly over years can reduce the sensitivity of the instruments. Frequency allocation and protection matter. Some bands are protected for astronomy, many bands are not. A transmitter that uses a band heavily used by communications may be impossible to detect from Earth due to strong human noise. A smart device can avoid bands used by humans and operate in frequencies that are less monitored by our instruments. Signal duty cycle is key. A device that transmits one short burst every many days is hard to catch. A device that transmits only when a relay passes or when conditions are right may be silent for long times. Surveys that scan for continuous beacons will not find rare bursts. Side lobe and spillover contamination can confuse searches. A signal can enter an instrument through an unexpected path. An event that enters through a spillover can be mistaken for a local source or for a far source. Such confusion can prevent proper follow-up. Processing assumptions shape searches. Pipelines assume models. They search for patterns that match known physics or known signals. A signal that does not fit the assumed model may be removed. The search methods thus favor known classes of events. Unknown classes can go unnoticed. Coordination across observatories is limited. When a candidate appears, getting multiple telescopes to look quickly is difficult. Telescopes are busy. Coordination protocols exist, but rapid multi-wavelength follow-up is not always possible. A brief event that needs fast follow-up may be lost if coordination fails. In sum, many technical and operational reasons cause current searches to miss small objects and rare signals. Sensitivity limits, cadence limits, frequency coverage gaps, data processing choices, and human and computing constraints all play parts. Hiding strategies used by devices exploit these same limits. Understanding these limits helps to design better searches and better tests for unusual signals. Knowing what our instruments and methods can miss guides the search for the faint and the quiet. Knowing where a device might hide tells us what signs to search for and what tests to run. Searches must look for many kinds of clues. They must also have clear checks to rule out errors and human sources. This chapter lists the practical signs that a small device could leave. It then gives step-by-step tests to use when a sign appears. The language is simple and the steps are direct. One clear sign is a narrow radio signal that stays on a single frequency. Natural radio sources usually spread their energy over a range of frequencies. A single thin tone is rare in nature. Many human transmitters make such tones. When a narrow tone appears, check the local radio logs first. Check for known satellites, aircraft, and ground stations that transmit near that frequency. Save the raw radio data. Reprocess the raw data with different filters. Ask a second radio telescope to monitor the same frequency at the same time. If a second telescope sees the same narrow tone from the same direction at the same time, the chance of a real distant source grows. Another sign is a pulse or burst that is very short and very bright. Such bursts can last only 1 millisecond or even less. To test such a pulse, keep the raw high-speed data if possible. Use a high-time resolution to see the shape of the pulse. Measure whether the pulse arrives earlier at high radio frequencies and later at low radio frequencies. This delay is called dispersion. If the delay follows the pattern expected from charged gas in space, the burst likely traveled through space. If there is no dispersion, check local sources. Also test the pulse for polarization. Measure how the electric field is oriented and if that orientation changes with frequency or time. Polarization is strong evidence of physical processes near the source. A repeating pattern is a strong sign to follow. If signals come in a repeating way, note the times between repeats. Measure whether the repeats come at a fixed period or at irregular intervals. If the period is constant, measure the period precisely and look for the same period in other bands. A repeating radio source that has the same timing in optical or X-ray bands points to a physical object that pulses. If the pattern is not steady, keep a long record and measure the distribution of times. Repeaters allow careful study. They let observers point many instruments at the source during active times. An unusual sweep in frequency can be a sign. Sweeps can be caused by the motion of the source or by changing conditions in the emitter. Measure the exact shape of the sweep. Test whether the sweep matches simple dispersion. If it does not, test models of moving transmitters. For moving objects near Earth, Doppler changes can shift frequency in a predictable way as the object moves. Measure the rate of frequency change. Use that rate to compute possible speeds. If the speed looks too high for a natural object at that size and distance, consider other explanations. A narrow spectral line in optical or infrared light can signal a molecular mesa or an unusual material. Record a spectrum of the source. Look for narrow lines that match known atomic or molecular transitions. If lines match water, hydroxyl, or other known massa lines, the emission may be a natural massa. If the lines do not match known transitions, record a higher resolution spectrum and ask instrument laboratories to cross-check stray features. If the optical spectrum shows metallic lines in the pattern not expected for rock, that point needs deeper tests. A sudden change in brightness of a small object is a sign to test. Photometric monitoring can show rotation, eclipses, or active emission. Take a sequence of images and measure how the brightness changes. Fit models of rotation to the light curve. Fast changes across a single rotation may show a reflective surface or a localized emission region. Compare the color of the light as the object changes. If the color changes in ways that suggest heated areas or active transmitters, then take spectra and infrared measurements. Radar returns that do not match natural shapes are important signals. Radar can give a rough shape and a measure of motion. A very flat, strong echo may mean a flat surface or a high reflectance. A radar echo that changes in a way that shows active stability control can show non-gravitational motion. Conduct multiple radar passes. Compare the echoes to models of tumbling rocks. If the echoes remain stable and the motion shows small periodic changes, test for possible station keeping or movement that needs small thrusts. Thermal emission can be a telltale sign. Measure infrared brightness as the object turns in sunlight. Fit a simple thermal model that uses the sunlight falling on an object of a given size and reflectance. If the measured thermal emission is larger than the sunlight can explain, test for internal heat. Internal heat can come from stored energy from chemical processes or from a radioisotope source. Take infrared images at different times of local day or during shadow to map the thermal pattern. Surface spectra tell about material. Take a reflected light spectrum to learn which minerals or metals are present. Rock and dust have known spectral shapes. Metals and alloys show lines that are different. If a spectrum shows features that are not produced by common geological processes, keep the data and ask chemists to test laboratory spectra. Send the sample pattern to other observers for independent checks. Orbital motion tests are key for nearby objects. Measure the position of an object many times and fit an orbit. If the orbit fits a gravitational solution with no extra force, the object is likely natural. If the fit requires extra acceleration that cannot be due to solar radiation pressure alone, test for outgassing or for thrust. Small, steady accelerations that change with time can mean a small propulsion system. For small objects, solar radiation pressure can cause measurable effects. Compute the expected radiation force based on the object size and reflectance. If the measured motion is inconsistent with this force, investigate further. Parallax helps locate distance. If observers at separated sites see a difference in the apparent position at the same time, use the difference to estimate the distance. For near objects, parallax can be large within sites separated by thousands of kilometers. For far objects, parallax is small. Triangulation between radio arrays or between optical telescopes gives a strong estimate of range for nearby candidates. Archive searches are powerful tests. Search past images and radio files for any sign from the same place. Look for faint, consistent traces. Old data can show weak repeating activity that a single observation missed. Do not rely only on catalogs. Go back to raw files if possible. New processing methods may find events that old software missed. Instrument tests are the first checks. Verify the clock and the timestamps. Verify that no maintenance or calibration action happened at the time. Check logs for human activity near the instrument. Power surges and software updates can create artifacts. Run the same data through different processing pipelines. If the event persists across independent pipelines, it is more likely real. Local interference checks are essential. For radio, check known satellites and their transmit frequency lists. Check aircraft flight logs. Check local radio and radar usage. Use directional antennas or multiple separated receivers to test if the signal comes from near the instrument. For optical events, check aircraft and satellite passes that can reflect sunlight. For infrared, check for ground heat sources or aircraft exhaust. For radar, check for radar crosstalk and for nearby active radars. Multi-wavelength confirmation is one of the strongest tests. Arrange for radio, optical, infrared, and X-ray instruments to observe the same position as soon as possible. A signal that shows up in more than one band is harder to explain as local interference. For a radio burst, a follow-up optical flash or a later infrared afterglow gives clear distance and host information. For a moving object, optical and radar together give size, shape, and motion. Use independent teams to confirm. Share the raw data with other groups. Independent processing removes the risk of a common software error. Independent observers can point different instruments. Independent checks build confidence. Record everything in a clear log. Save raw files. Note instrument settings, weather, and human activity. Record the exact time in a standard time scale. Record the position and the beam that saw the signal. Note any automatic filters used in real time. Keep a copy of the unprocessed data separate from processed files. Design a step-by-step response plan for any candidate. The plan should list who to call, which instruments to request, and what immediate checks to run. The plan should include a checklist to rule out local human sources. The plan should set thresholds for rapid alerts. The plan should require saving raw data for at least 1 year. The plan should list the archive locations and the person responsible for each file. For radio bursts, keep baseband recordings when possible. Baseband data let analysts apply more precise dedispersion and timing tests. They let observers check whether the burst is coherent across a wide band. Coherence and stable phase behavior are important clues for artificial signals. If baseband data are not saved, note the sampling rate and the filtering used. For optical transients, take rapid images to localize and then point larger telescopes for deeper images and for spectra. A spectrum gives a redshift if the source is far. A redshift gives distance. Distance tells how much energy the event needed to be bright. For nearby objects, spectra identify minerals and materials. For infrared tests, use long integrations to map thermal emission over time. Measure how the thermal emission changes with local time. If the object warms and cools in ways that do not follow sunlight, test for internal heat sources. Map the thermal pattern across the surface if possible. For radar tests, aim multiple passes to build a shape model. Use the radar echo to measure rotation. A steady rotation rate that changes predictably can show influence by small thrusters. Sudden changes in rotation may signal collisions or active attitude control. Use timing networks for localization. If radio telescopes at several sites record the same short burst, use the timing differences to triangulate the direction precisely. Very precise clocks and careful calibration are needed. Successful triangulation can reduce a large error region to a small patch, allowing optical telescopes to point and search for a counterpart. Test for coding or information content. If a signal is narrow and shows structure, test whether the signal carries repeatable patterns. Use simple tests for periodicity and for repeating sequences. Use algorithms that test for non-random structure. If structure repeats with a pattern that is not known in nature, keep the data and share with experts in signal analysis. Estimate physical energy when distance can be measured. For a radio burst seen far away, compute the energy required to produce the observed signal. If the energy is very large, test whether known natural processes can deliver that energy in a short time. If natural processes cannot explain the energy, document the calculations and seek independent review. When tests are complete, classify the finding. Use categories such as likely human interference, likely known natural source, unknown natural source, and unexplained afterchecks. Keep records of which tests were run and what the outcomes were. Be open about what was not tested. Share unusual findings carefully. Do not make wide public claims before cross-checks are done. But do share data with qualified teams who can test the results. Use secure channels when necessary. Clear and honest communication speeds validation and reduces false alarms. Plan for long-term monitoring. Some sources repeat only after long, quiet times. Keep the position on watch lists. Schedule follow-up observations at times when the source showed prior activity. Keep reprocessing archives for new methods that may find signals missed before. Train teams to run the tests. Make simple checklists that any operator can follow when a candidate appears. Practice drills with simulated signals. This training reduces mistakes and speeds real responses. Use shared catalogs to mark positions that had odd events. A simple database with the position, time, instruments, and test results helps future searches. When different teams record weak, consistent hints at the same position, the combined evidence grows. Keep improving tests with new methods. Machine learning can help find patterns, but always test machine-based results with independent pipelines. Update the filters and the search ranges as human activity changes the radio and optical sky. Test pipelines with known signals to avoid losing novel events. The tests above are practical and simple. They cover radio, optical, infrared, and radar methods. They check instruments, local sources, archives, and independent confirmation. They measure timing, spectrum, polarization, and motion. They preserve raw data and the logs. They use networks of observers and clear checklists. These signs and tests do not promise quick answers. Many puzzles take time and many repeats to solve. The goal is to be thorough and to keep clear records. Careful work makes it possible to find real rare signals and to rule out false ones. The next step is to use these tests to build search programs that watch in many ways and for a long time. Using these tests, a strong search program must be built with many parts that work together. A program must watch the sky for a long time. It must use many instruments. It must store and share data. It must have clear rules for checks and for alerts. It must train people to run the work. Below are the simple steps and the parts needed to build such a program. Start with a clear goal. The goal can be to find small devices or to find any unusual signal. Write the goal in plain words. The goal guides what instruments to use. The goal sets priorities for time and money. Choose the right instruments. Use radio arrays to listen across wide frequency ranges. Use single-dish telescopes for sensitive narrow-field work. Use optical survey telescopes to scan large areas of sky. Use fast optical cameras to catch quick flashes. Use infrared cameras to measure heat. Use X-ray and gamma-ray instruments to watch high-energy events. Use ground radar to probe nearby rocks. Put some instruments in space to avoid the noise from the atmosphere and from human activity. Each instrument finds a different kind of signal. A strong search program uses many of them. Make a plan for where each instrument watches. Some will scan the whole sky slowly. Some will watch a small patch very deeply. Some will point at known objects often. Some will follow alerts and point quickly. Decide which parts of the sky need constant coverage and which parts can get sparse coverage. Set a mix of broad and deep coverage. Build a schedule that allows fast response. Some events last only moments. A network of telescopes must be ready to point in minutes. Robots and remote telescopes can repoint quickly. Have a list of telescopes that can respond fast. Include small telescopes that can start observations while larger telescopes get ready. Fast response increases the chance to collect multi-band data. Set up long-term monitoring. Some signals repeat after long gaps. Keep watch lists of interesting positions. Schedule repeated observations over months and years. Keep data to find slow trends and rare repeats. Long-term work finds patterns that short campaigns miss. Make redundancy in the instruments. Have more than one radio array and more than one optical telescope cover key parts of the sky. Redundancy helps confirm events. If one instrument fails, another can still watch. Redundancy also helps to rule out local interference. Design the data pipeline carefully. Raw data must be saved for a useful time. Raw files are the ground truth. Store raw files and processed files. Include logs that show instrument settings, software versions, and any maintenance events. Record the exact time in a single standard timescale. Use coordinated universal time for all timestamps. Include precise position data for pointing and beam shapes. Use standard formats for data and metadata. A common format helps teams share files and tools. The format should include the raw measurement, the calibration files used, and the processing steps applied. Keep a clear record of any flags applied. A future reprocessing must be able to start from the raw files. Build automated detection systems. Use software to scan data and flag candidate events. Design the software to run many tests. Let it measure brightness, spectrum, timing, and shape. Set thresholds that are strict enough to limit false alarms. Also set a lower threshold list for rare manual review. Let the software mark events that fail some automated test but are unusual in other ways. Do not let any single filter throw away raw files. Include human review. Machines can flag events, but people must inspect unusual cases. Train teams to review the candidates. Make a rotation schedule so trained reviewers are always available. Keep simple checklists for the review. The checklists should cover instrument status, local interference, reprocessing steps, and archive checks. Share data across teams quickly. Create an alert network that distributes essential information. Each alert should include the time, the position, the instrument that detected the event, and basic measurements. Include links or pointers to the raw files and to instrument logs. Use secure channels when needed. Use open channels when rapid global help is useful. The alert should be clear and short so other teams can act fast. Define levels of alert. Use a simple scale for priorities. A low-level alert is a routine candidate that needs more checking. A medium-level alert asks for follow-up by other instruments. A high-level alert asks many teams to respond quickly. Set rules for how to upgrade or downgrade the level as tests are run. Keep the criteria public among the teams. Plan multi-wavelength follow-up. Many instruments must act together. Create agreements and protocols so teams can point telescopes quickly when needed. Set aside some observing time for rapid follow-up. Have pre-arranged contact chains so a coordinator can reach the right people fast. Use clear messages that state the urgency and the specific actions requested. Protect some radio bands for quiet observation. Work with regulators to keep certain frequency windows free from strong human transmissions when possible. Ask for protected observation times for key instruments. Make radio quiet zones around sensitive observatories if feasible. Coordinate with satellite operators to reduce bright reflections during critical observation windows. Design the program to reprocess old data. New methods will find events missed by earlier software. Keep raw archives and reprocess them periodically. Schedule blind reprocessing runs with updated pipelines. Keep a record of which runs were done and with which software versions. Reprocessing can find repeating sources that first appeared as weak hints. Build a public catalog of candidate events. List positions, times, instrument measurements, and what checks were run. Mark the status clearly. Make the catalog searchable. Let other teams add results from their follow-up. A public catalog helps many groups compare notes and combine weak hints into a stronger case. Set clear standards for reports. Each report must list the raw files, the processing steps, the instrument settings, and the checks for local interference. Include the names of the people who ran the checks. A standard report saves time and avoids confusion. Use simple forms that any team can fill. Train people with drills. Run simulated events so teams practice the response. Include false alarms in the drills. Practice helps teams run the checklists quickly and without error. Keep the drill results to improve the procedures. Training reduces mistakes when real events occur. Protect the data and the privacy of operations. Some raw files may include sensitive information about national infrastructure. Follow laws and policies for secure data. Share data with trusted teams when needed. Keep a public summary that does not reveal secure details. Plan for computing needs. Searching for fast events requires large compute power. De-dispersion, fast Fourier transforms, and image stacking take many cycles. Provide servers and storage that can scale. Use cloud resources for occasional surges. Keep a plan to fund and manage the compute infrastructure. Use careful statistics. Set thresholds that control the rate of false alarms. Account for the number of independent trials when testing significance. If the search looks at many frequencies and many times, adjust the criteria so that rare random spikes do not trigger many false positives. Publish the statistical methods and the thresholds used. Design pipelines to test themselves. Inject fake signals into the data to check that the software finds them. These injections measure the sensitivity. Vary the fake signals to test different types of events. Record which injected signals were found and which were missed. Use these tests to tune the detection thresholds. Make the program global. Include teams from many countries. Global coverage helps follow up quickly across time zones. It also brings different instruments and local knowledge. Global cooperation spreads the cost and increases the chances of success. Create standards for cross-checking. Define a minimum set of tests that must be run before an event is called confirmed. The tests should include instrument checks, local interference checks, independent detection, and basic multi-wavelength follow-up when possible. Keep the standard public. Teams can then plan to meet it. Record and publish null results. When searches find nothing, publish the coverage and the limits achieved. Null results tell others where to adjust their plans. A clear record of coverage, sensitivity, and time allows the community to fill gaps more efficiently. Plan long-term funding and maintenance. Search programs need steady money for years. Maintain instruments and replace parts. Keep skilled staff. Plan for upgrades. Short funding cycles hurt the ability to build long-term catalogs and to follow rare events. Build a flexible governance model. Make a small board or steering group that sets policy. Include scientists, data managers, engineers, and ethics advisors. The board should set standards for data sharing, for public alerts, and for response to unusual events. Keep decisions transparent and recorded. Include ethics and risk review. If an event looks like it might involve an artificial source, ethical and safety questions arise. Have a group that can advise on caution in public statements and on the handling of possible contact. This group should have clear procedures and a list of people to consult. The group should coordinate with national and international bodies when needed. Encourage open science, but be cautious. Share raw data and methods with qualified teams. At the same time, avoid premature public claims that cause confusion. Require that any public release includes the tests run and the level of confidence. Coordinate with existing facilities. Work with radio arrays, optical surveys, radar facilities, and space agencies. Use their experience and their instruments. Ask for access to data archives. Build partnerships so that the program can use the best tools available. Make space-based assets part of the program. Put radio and optical sensors in orbit to find signals that ground-based systems miss. Space sensors can look near the sun and can avoid atmospheric noise. Place instruments at stable points and in low Earth orbit. Plan for relays and downlink bandwidth. Design a network of small detectors in space. Small satellites can provide wide coverage. They can monitor for flashes and for radio bursts. A constellation of small sensors can multiply the coverage and act as a distributed alert system. Plan for near-Earth object searches. Include radar campaigns and optical scans that target small rocks and mini-moons. Use dedicated surveys that can find faint and fast-moving objects. All sky surveys can be tuned to detect faint small bodies if enough observing time is available. Protect the program from growing human noise. Monitor the growth of satellite constellations and new transmitters. Update strategies to handle new kinds of interference. Work with regulators to limit harmful emissions in key bands. Set a clear path for raising and lowering the alert level. The plan should include who decides, what tests must be run, and how other teams are notified. Clear rules reduce confusion when an event occurs. Use common tools and open-source software when possible. Shared tools reduce duplication. They let teams review each other's pipelines. Keep software repositories public and document all code. Keep good records of every candidate. For each event, file a summary that includes who reviewed it, what tests were done, and the final status. A searchable database of candidates and their outcomes helps the community to learn. Build public outreach plans. If the program finds an unusual signal, the public will need clear and calm information. Plan simple public statements that explain the facts and the steps taken. Avoid technical jargon. Keep the public informed in a factual way. Adapt and learn. As new signals and new noise sources appear, update the search plan. Do not lock the program into one narrow method. Allow new instruments and new ideas to join. Finally, make a plan for action when a clear, unusual signal appears. The search program must list the immediate steps to confirm the finding. It must name the contacts, the instruments to call, and the tests that must run quickly. It must also include the rules for public communication. A program that combines many tools, clear procedures, global cooperation, and long-term care is the best way to find and to study rare and faint signals from space. If a clear, unusual signal appears, following these plans gives the best chance to check it carefully and to gather the data that will lead to a sound conclusion. When a clear, unusual signal appears, the work that follows must be calm and careful. The first minutes and hours set the path for a strong result. Teams must follow a plan that saves data, checks instruments, and asks others to help. The actions fall into 4 groups: save and protect the data, check and test the instruments, confirm the signal with other observers, plan communications and ethics steps. Each group has clear tasks and a simple order to follow. Save and protect the data right away. Stop any automatic deletion of raw files. Make copies of the raw data and store them in separate physical places. Label each copy with the exact time in coordinated universal time with the instrument name and with the settings used. Keep the original files untouched. Make a checksum or a hash for each file so later teams know the file has not changed. Keep a written log of who handled any copy and when. Do not let routine cleaning scripts remove any related files for at least 1 year. Check the instrument that first saw the signal. Look at the instrument logs for the minutes and hours before the event. Note any maintenance, calibration, or software update that ran at that time. Check the hardware state. Read voltages, temperatures, and clock sources. Confirm the timestamp on the data by checking the observatory clock against a reference clock. If the instrument uses GPS or another time service, check the service logs too. If a problem is found in the instrument or in the clock, mark that clearly in the record and alert other teams. Run an immediate reprocessing of the raw data using an independent pipeline. Use different software and different filters from the ones that first flagged the event. If possible, run the reprocessing at a separate site. Compare the outputs. If the event appears in both processing paths, that increases confidence. Save both processed outputs and the scripts used to create them. Note any differences and keep the versions of the software that produced each output. Check for local interference and human sources. Compile a list of all likely transmitters and activities near the instrument at the time. Check satellite ephemerides and look for any satellite passes in the line of sight. Check aircraft tracks over the observatory. Check for any radar sweeps from local or regional sources. Check for transmissions from ground stations, from mobile phone networks, and from maritime and aviation radios. Check the observatory site for any local equipment that could radiate. Speak to the staff on site to learn if any tests or systems were active. Record all findings. Call and ask other observatories to search their records immediately. Provide the exact time window and the sky coordinates. Ask radio arrays, optical telescopes, infrared cameras, X-ray and gamma-ray instruments, and radar facilities to look for a signal at that time and place. Ask them to check their archives first and then, if possible, to point at the target for real-time follow-up. Use a clear and short alert message that lists the time, the coordinates, the reported frequency or wavelength, and the best contact person. Do not make public announcements until independent checks are underway. Try to get an independent detection quickly. One independent detection can change the status of the event. If another radio telescope sees the same signal at the same time from the same sky direction, the chance of a local instrument problem drops. If an optical or infrared flash appears at the same place, that helps to locate the source. Radar echoes from the same direction can provide distance and motion. Independent detections from different methods are the strongest immediate step. Measure the key properties of the signal carefully. Record the exact frequency or frequencies, the bandwidth, the total duration, and the fine time structure. Measure the polarization and how it changes with frequency and time. For radio signals, measure dispersion and the sweep of arrival time across frequency. For optical and infrared signals, measure color changes and the rise and fall times. For radar returns, measure the delay, the Doppler shift, and the echo strength. Keep all measurement scripts and report the uncertainties in each number. Search catalogs and archives for known sources. Check catalogs of pulsars, of active galactic nuclei, and of masers to see if a match exists at the same coordinates and frequency. Check lists of satellites and of planned launches. Search past images and radio files for any faint signal at the same place. If the signal matches a known source, document the match and the reasons. If no match exists, keep the case open and record the negative results. Estimate distance using available methods. For radio bursts, use dispersion to infer the amount of charged material the signal passed through. Compare the measured dispersion to models of the local galaxy to see whether the source is likely in our galaxy or beyond. For optical bursts, take a spectrum and measure any redshift. For radar detections, use the return time to measure distance. Use parallax between two separated observatories if possible. Write down the assumptions used in any distance estimate. Compute the energy needed to make the observed signal at the estimated distance. For every band, use a simple formula to convert the measured flux to energy output. Keep the units clear and avoid hidden constants. If the energy is extreme for a single short pulse, document that result and how it was calculated. Have independent teams run the same calculations and compare results. Run tests for natural causes that can make similar signals. For radio signals, test for maser lines, for plasma emission, and for known pulsar or magnetar behavior. For optical flashes, test for supernova, for flare stars, and for reflected sunlight from a moving object. For infrared excess, test for internal heat sources like radioisotope decay or chemical reactions. For every test, list what would match the observation and what would not. Run tests for instrumental artifacts. Recreate the same instrument state in a lab or on a test bench if possible. Inject known signals into the instrument to see if the pipeline might create a false positive. Watch for software bugs that may create spurious lines or spikes. Try changing the clock or the calibration and rerun the processing. If the event disappears under all reasonable reprocessing, mark it as doubtful and record why. Look for repetition. Schedule long monitoring of the source position. Many unusual objects repeat. A repeating signal gives time to run many tests and to gather multi-wavelength data. Keep a watch list and schedule observations with different instruments at different times of the day and night. Note the intervals between bursts and the distribution of burst strengths. Use simple histograms of waiting times and amplitudes. Let the pattern guide the next tests. Localize precisely. Use arrays or simultaneous observations at separate sites to triangulate the position. For radio bursts, use timing differences between widely spaced antennas to reduce the error region. For optical targets, use deep imaging to find a counterpart in the localization area. A precise position lets teams search for a host galaxy or for a small object near Earth. If the position points near Earth, shift the tests. Use radar to search for a nearby object. Use high-cadence optical imaging to find fast-moving objects. Use infrared cameras to map thermal emission from the candidate. If a nearby object is found, measure its orbit and the reflectance properties of its surface. Also measure whether the object shows non-gravitational motion that would need thrusters or active attitude control. If the position points to a distant object, plan spectroscopic follow-up. Obtain a spectrum and measure lines that give redshift and chemical composition. Use the spectrum to test models of explosion physics or of accreting black holes. Share the spectrum files widely and keep raw counts and calibration frames for reanalysis. If the signal shows narrow frequency structure or coding like repeated patterns, test for information content. Use simple statistical tests to see if the pattern is random or if it carries structure. Test for repeated sequences, prime number patterns, or repeated symbol sets. Apply many common signal processing tools and share the raw baseband data with trusted independent teams for deeper analysis. Form an internal advisory group quickly. This group should include instrument experts, data analysts, astronomers, ethicists, legal advisors, and communications specialists. Keep the group small and focused at first. The group must keep a clear log of decisions and of who has access to sensitive files. Use the log to track what checks were run and their outcomes. Manage communications carefully. Designate a single point of contact for public statements. Prepare short messages that state the facts and clearly list what is not known. Avoid speculation and avoid exaggerated language. Explain that checks are ongoing and that more data are being requested. If the signal affects safety or national infrastructure, inform the relevant authorities in a private and secure channel as required by law. Decide on data sharing rules. Share raw data with qualified teams that can run independent checks. Use secure channels for early sharing if the files contain sensitive information. At the same time, prepare an unclassified summary that can be released publicly. Make the criteria for wider public release part of the plan that the advisory group agrees on. Consider ethical and safety questions. If the signal could be artificial, prepare a larger review with broad representation. That review should include more scientists, policymakers, and ethicists. The review must test whether any reply or any action to contact the source is advisable. Create a checklist that asks about the risk to people and to infrastructure. Record all opinions and the reasons behind them. Do not reply to a possible artificial signal without wide and agreed processes. Any outbound transmission raises policy and ethical issues. If a reply is considered, decide who has the authority to send it. Establish a multi-institutional committee that includes international partners. Set strict rules for message content and for transmission methods. Include a requirement for public transparency after a decision is made. Coordinate with international bodies and with national agencies. When an event is credible and not solved by normal tests, inform the appropriate agencies. Use official channels for space and for science. Provide the records, the data, and the analysis. Ask for assistance from other observatories and agencies. Prepare a long-term plan for study. Unusual signals may need months or years of follow-up. Schedule continued observations. Reprocess archives as new methods appear. Keep the position on watch lists. Extend the monitoring to other wavelengths and to radar if needed. Keep the public informed in a clear and honest way. Give the basic facts. Say clearly what tests were done and what the results were. State the level of confidence. Explain the next steps. Avoid statements that promise immediate answers. Provide regular updates as new checks come in. Record and publish the final analysis. When the teams reach a clear conclusion, publish the data, the methods, and the tests. If the source is natural, explain which tests led to that conclusion. If the source remains unexplained after thorough checks, publish the results with the list of tests that were run and the open questions that remain. Publishing the full record allows the wider community to test and to learn. Train and practice these steps before an event happens. Run drills that include instrument failure and false positives. Practice communications and the chain of custody for data. Keep templates for alert messages and for public statements. Practice helps reduce mistakes under stress. Plan resources for rapid response. Keep computing power and storage available to process raw files quickly. Keep contacts ready at many observatories. Reserve small blocks of observing time for urgent follow-up. These resources reduce delays in confirming or rejecting a candidate. Finally, keep the attitude of careful science. Simple, clear tests done in the right order give the best chance to find the truth. Avoid rushing to dramatic claims. Save the raw data. Check the instruments. Ask for independent confirmation. Use many tools and many experts. Work openly and honestly. The goal is a solid answer based on strong evidence. That path is slow and steady, but it is the correct way to handle any clear, unusual signal from space.